Hey everyone, now I will present problem 9 from this year's TST. Incidentally, this is harder than problem 10 because it is the only problem in the test that no one solved, which to my great disappointment because it was a problem that I wrote. Okay, what is the volume of the three-dimensional solid formed by folding the net below? Each triangle in the net is an equilateral triangle of side length 2, as is indicated here. Okay, how do we begin to approach this? So when we fold a net, this vertex maps to this vertex. This vertex, when I say map, I mean as in they come together. This vertex comes to this vertex. This vertex comes to this vertex. I should have arrows. Because they come together. So what does this form? So to help me visualize, what I did is I put this triangle here as the base. Maybe I should use red. This triangle is the base here. I set the net flat on the table. Well, like in my imagination, of course. And this triangle lies flat on the table. And then these triangles on the edges fold up into the air. And then this triangle here, which is in blue, this edge comes up over here. So then this edge connects this vertex and this vertex. Similarly, this edge connects this vertex and this vertex, and this edge connects this vertex with this vertex. Right now we are ignoring the triangles on the outside here. Okay? So, I will now present to you my very badly created drawing that is created when you fold these 7 triangles on the inside in this manner. You get this shape. So the red triangle is the base. The marked blue triangles are the triangles that come up. In particular, they are these triangles here. These ones. And then the black edges are ironically the edges that are marked in blue here, the ones that connect these vertices. So those well-versed in 3D geometry will recognize this shape as an octahedron, which is one of the 5 basic platonic solids. And to find the volume of this octahedron, we can reorient it so that these 4 edges are a square parallel to the table. So that would look like this. From this, it is clear that this octahedron is in fact 2 square pyramids stacked one on top of the other. We will find the volume of this octahedron later, because now we must account for a mistake that unfortunately many of you made. On the previous slide, we ignored these 3 triangles on the exterior here. What change does these 3 triangles make? Notice that the 3 edges marked in blue here, they come together to form this black equilateral triangle at the top, right? So then these equilateral triangles on the outside form an additional regular tetrahedron on top of this black triangle on top, like this. So our final shape is an octahedron plus a regular tetrahedron attached to one face. And we want to find the combined volume of these 2 solids. So that is what we will now do. Recall that the side length of both of these objects is 2. Let's start with the octahedron. So we know the square base of the square pyramid of the octahedron has area 4. And now we want to find the height. So we take the cross-section that consists of this square going this way, where this line is the table, this is 2, and we want to find this height. From this is apparent that the height is the square of 2. So the volume of the square pyramid is base times height over 3, which is equal to 4 times square root of 2 over 3. Because we have 2 of these square pyramids, the volume of the entire octahedron is 8. 8 times the square root of 2 over 3 for the octahedron. Now we want to find the volume of the tetrahedron. So the equilateral base, I could derive the equilateral triangle area, but it is handy for many of you to remember the formula side length squared times the square root of 3 over 4. So in this case, the area of that equilateral triangle will be the square root of 3. Now we want to find the height of the tetrahedron. Now we take the cross section corresponding to the midpoint of this side here, this vertex, and this top vertex. So what does that give us? So this is a side length tetrahedron. We know it has side length 2. This is an altitude of the equilateral triangle. The altitudes of the equilateral triangle each have length square root of 3 because these form 30, 60, 90 triangles. Now we want to find this height of this triangle. Again, we can use the area of this triangle. Let's go into the next slide. As just to copy over, 3 root 2, we want to find this height. The base is square root of 3, and the octahedron has volume 8 times the square root of 2 over 3. So let's find the height of this tetrahedron, or from this cross-section, the height of this triangle. So we'll first find the area of the triangle, and to find the area of the triangle, we take the other altitude going this way, which is much easier to find because it's an isosceles triangle. So this side length of this right triangle here is 1, so this side length here must be square root of 2. Thus, the area of this triangle is 2 times the square root of 2 over 2 equals 2 roots. Now, if we let this be h, the height of the tetrahedron, then we have h times the square root of 3 over 2 is equal to square root of 2. So h is equal to 2 times the square root of 2 over the square root of 3. Now, once again, we can use the volume of the tetrahedron is base times height over 3. So that should give you 2 times square root of 2 over 3 roots times 3 roots, once again all over 3, which is 2 times the square root of 2 over 3. Thus, our final answer, adding these two values, is 10 times square root of 2 over 3. And we're done.